Up to now, we've developed the Generalized BlackScholes model for multiple assets using a multidimensional standard Brownian motion to model the dynamics of the underlying assets. The components of this Brownian motion are independent, and the number of components is the same as the number of risky assets. In other words, the dynamics look something like this in the two-dimensional case. Here each asset has its own drift, but it also has a volatility vector. So for example, sigma 11, sigma 12 is the volatility vector of S1. Now it is often convenient to rewrite the dynamics in a decoupled fashion as follows, where each asset still has the same drift, where each asset has its own volatility number, sigma hat, rather than volatility vector, and is driven by its own Brownian motion, W hat, which is one-dimensional. In this case, the Brownian motions W1 hat and W2 hat are correlated. Such a setup may be simpler because each asset is now driven by only one source of noise. For example, if we have such a model with two assets, but we'd like to price an option on just one asset, say on S1, then we will need to know the volatility of the asset S1. That volatility is the number sigma 1 hat. It's not obvious from the two-dimensional formulation what the volatility number is. We're given a volatility vector. But the BlackScholes formula for call options, for example, requires a volatility number, not a vector. In order to rewrite the dynamics of the assets using correlated Brownian motions, we'll have to determine the volatility numbers sigma 1 hat and sigma 2 hat, as well as the correlation rho between W1 hat and W2 hat. And these should be determined from the original formulation using an independent standard Brownian motion. Before we continue, let's recall how to generate a multidimensional correlated Brownian motion. We'd like to generate a Brownian motion W with components W1 up to WK, where the correlation matrix of this Brownian motion is R with components rho ij. Remember that a correlation matrix is just a special kind of covariance matrix, and that a correlation matrix always has ones along the diagonal. Since a correlation matrix is symmetric and non-negative definite, it must have a Cholesky decomposition. Let C times C transpose be the Cholesky decomposition of the correlation matrix, where C is a lower triangular matrix. Also generate a standard Brownian motion, B, with the same number of components, namely K, but with independent components. Then define W to be the matrix C times the vector B. If we then compute the covariance matrix of W, by definition, it's just the expectation of W times W transpose, because the mean of W is 0. And if we use this equation over here, that reduces to the following, where the expectation in the middle is just the covariance matrix of B. But because B has independent components, that's a diagonal matrix with just the variances of the Brownian motions along the diagonal. And because the variance of a Brownian motion is the elapsed time, we obtain that the covariance matrix of W is C transpose times T, which is the same as R times T. It therefore follows that the correlation between two components Wi and Wj is just the covariance between Wi and Wj divided by the standard deviations of Wi and Wj. I remind you again that R has ones along the diagonal, and so the variances of the components are equal to T, and hence their standard deviations are the square root of T. And when we simplify this, we obtain rho ij. In other words, the correlation between Wi and Wj is indeed rho ij, which means that the correlation matrix of the multidimensional Brownian motion W is capital R. Now observe that dWi times dWj is just this sum here, but dBk times dBl is 0 if k is not equal to L, because bk and bl are independent. It's equal to dt when k is equal to L, and hence this sum over two indices simplifies to a sum over just one index where k is equal to L. Now this sum here is just the ij component of C times C transpose, and so dwi times dwj is equal to rho ij dt. This means that the quadratic covariation of wi with wj is rho ij times t. In particular, if I is equal to j, then the quadratic variation of wi is just equal to t, because rho ii is equal to 1. Since wi is clearly a continuous martingale and has quadratic variation equal to t, each wi is a one-dimensional Brownian motion, as required by Levy's characterization of Brownian motion. Suppose that we have acid dynamics in the standard setup using a multi-dimensional Brownian motion to model the noise. To simplify notation, we've just used two acids, but of course this generalizes to any number of acids. Here, the standard Brownian motion has independent components, and it affects each of the two underlying acids. In other words, each acid is driven by two sources of noise. We want now to rewrite these dynamics in a decoupled fashion as follows, where each acid has its own one-dimensional Brownian motion that is driving it, and these Brownian motions, W1 hat and W2 hat, are correlated with correlation rho 1, 2. Equating the two expressions for the acid dynamics, we see that we must have the following. Equating these two expressions for the acid dynamics, we see that we obtain the following. Now we can cancel the dt terms, because these are the same on both sides of the equation, and hence we're left with the following system. Sigma 1 hat dw1 hat is equal to sigma 1 1 dw1 plus sigma 1 2 dw2, and similarly sigma 2 hat dw2 hat is equal to sigma 2 1 dw1 plus sigma 2 2 dw2. Now let sigma n denote the volatility vector of the nth acid, in other words the nth row of the volatility matrix sigma. Recall that dw1 times dw2 is equal to 0 because w1 and w2 are independent, but that dw1 hat times dw2 hat is equal to rho 1 2 dt, where rho 1 2 is the correlation between w1 hat and w2 hat. If we now compare the quadratic variations and covariations of the left-hand side and the right-hand side here, we obtain the following. The quadratic variation of the left-hand side of the first equation is just sigma 1 hat squared times dt, shown here. On the other hand, using the fact that dw1 times dw2 is equal to 0, the quadratic variation of the right-hand side is sigma 1 1 squared plus sigma 1 2 squared times dt. Now sigma 1 1 squared plus sigma 1 2 squared is just the length squared of the volatility vector sigma 1. In the same way, if we look at the quadratic variation of the second equation on the left and on the right, we obtain sigma 2 hat squared dt and sigma 2 1 squared plus sigma 2 2 squared dt respectively, where again this expression here is just the length squared of the volatility vector sigma 2. In other words, the length of the second row of the volatility matrix. The covariation is obtained by multiplying sigma 1 hat dw1 hat with sigma 2 hat dw2 hat, and using the fact that dw1 hat times dw2 hat is equal to rho 1 2 dt, we see that the covariation of the two processes on the left is given as follows. Similarly, the covariation of the two processes on the right is obtained by multiplying them and looks as follows. Now sigma 1 1 sigma 2 1 plus sigma 1 2 sigma 2 2 is just the dot product of the volatility vector sigma 1 with the volatility vector sigma 2. Hence from these equations we obtain the following. The volatility number, sigma 1 hat, is just the length of the volatility vector, sigma 1. The same holds for sigma 2. The correlation rho 1 2, which we can obtain from the third equation, is given as follows. Sigma 1 dot sigma 2 divided by the length of sigma 1 and the length of sigma 2. Of course, it is easy to see how this generalizes to more acids and higher dimensions. Let's end now by considering the BlackScholes PDE with correlated Brownian motions. We have a multi-acid BlackScholes type model with capital N many acids, Sn, and an equal number of correlated Brownian motions, W hat n. So in decoupled form, we assume that the dynamics of the underlying acids are given as follows, where we have a volatility number, sigma hat n, and a one-dimensional Brownian motion. And in standard form, using a multi-dimensional standard Brownian motion, the dynamics look as follows. The correlation between W hat n and W hat m is defined to be rho nm. Now we've seen that sigma n hat is just the length of the corresponding volatility vector, and that the correlation is given as follows. Note that sigma n dot sigma m is just the nth row of the volatility matrix dotted with the mth row, which is the same as the dot product of the nth row of the volatility matrix with the nth column of its transpose. In other words, it's equal to the nm element of sigma times sigma transpose. Moreover, the lengths of the volatility vectors are the corresponding volatility numbers. Now earlier, using independent Brownian motions, we obtained the following multi-acid BlackScholes PDE. And in order to rewrite this using one-dimensional volatilities and correlations, we just have to deal with this number here, namely the nm component of sigma times sigma transpose. If we go back to this equation here, we see that that component is precisely rho nm times sigma hat n times sigma hat m. And thus replacing this number, we obtain the following BlackScholes PDE.